启动直播了。
还没，再等一下。好。
喂，各位，可以吗？听清楚吗？ Hello， 可以听清楚吗 ？Hello， 远端可以听清楚吗 ？Hello， 远端可以听清楚吗 ？Hello， 远端可以听清楚吗？
应该是可以的。
可以的哈。OK， 好。Let us begin our last class of this semester. Next week will be our final exam. I add 3 slides in this set of notes. You can download it from our site called Predictive 2015. Go there to download it. I installed a few slides in that new revised lecture note. This is one of them. Assume that we have input-output relationship that's related to relate the output from k minus 1, k minus 2 to k minus p to the input k minus 1 to k minus p. This is what we call finite difference model. If we set this is p, we set k equal to 0, then y0 equal to beta 0 u0, and set up k equal to 1 and y1 equal to minus r1, y0 beta 0 u1, beta 1 0, and so on. So you have up to as many as the number of data you have. So we call the last one called L. All right, let us just give an example. Let's p equal to 1, and this is the model. Yk plus alpha 1, yk minus 1 equal to beta 0 uk plus beta 1 uk minus 1. So that's p equal to 1. Of course, that most likely that p won't be equal to 1, will be like 10 or 30 or 50. But let us just example p equal to 1. Then one obtains the y0 equal to beta 0 u0. And then y1 equal to minus alpha 1 y0 plus beta 0 u1 plus beta, oh that's wrong, beta 1 u0. So this is supposed to be beta 0 here, not beta 1, not beta 0. And then the y2 equal to minus r1 y1 plus beta 0 u2 plus beta 1 u1. And y3 equal to minus alpha 1 y2 plus beta 0 u3 plus beta 1 u2, and so on. So up to I say my total number of data will be only 5. That's the 5 there. And so if we rearrange this equation of motion to become like this, we put y0, y1, y2, y3, y4, y5 into one row. But this y, each y can be a column vector. That means for this case, that if y, we have only one sensor, assume we have one sensor, then y will be only a scalar. If we have two sensors, then y will be 2 by 1 column vector. So this will be 2 by 1 if we have two sensors. If we have 3 sensors, then y0 will be 3 by 1. Then y1 will be 3 by 1 too. So this is not only a scalar in general. But here, if we assume they are just a scalar, then we can write y0, y1, y2, y3, y4, y5. And then my parameters are beta 0, beta 1 minus beta alpha 1. If I put this as this order, then the right-hand side of these equations, we can write in terms of u0 and 0, 0, that's my y0. See, my y0 equal to beta 0, u0. So my y0 equal to beta 0 times u0, beta 1 times 0 minus alpha 1 times 0. So that's u0. And then my y1 will be alpha 1, y0, beta 0, u1, and beta 1, u0. So if you look at this, y1 will be beta 0, u1, and then beta 1, u0, and then alpha minus alpha 1, y0. So that's here. Then the same thing, y2 will be this times the third column of this. Then y4, y5, the same thing. So we form this kind of matrix here. This matrix is a matrix just for p equal to 1. Now, of course, if p equal to 2, then we'll have more rows, not just only column here. We'll get more rows. For your homework problem number 10, I assume p equal to like a 2 there. Model size equal to 2, and I have one sensor, one output. So in your last homework, I say assume model size equal to 2, but my output is only equal to 1, so p really can be equal to 2. Yeah, so that's a different than just 1, but that's the same thing. You can just put like this way. Okay, now if we assume if we put the u0 and y0 to become v0, if we put u0 and y0 together and we define u0, y0, the column as a v0. Okay, so that means I put u and y together. I define that equal to v, and then this become a v, and the same v1, v2. All right. Now this is p equal to 1, and this is really simple, just example. Now for system ID, the same thing, we'll be able to find y0 equal to y0, y1, y2, yp, l minus 1, and we can form v, and that v, just like the last example, we have like a v like there. Then we can have v, I call v equal to u, k, yk, the small v. And finally, we'll be able to form this, to solve the y bar equal to that alpha. This is y bar is all the parameters we want to solve. Okay, and then here I add one more example. This is my example. That's an example. I say u equal to 1 minus 1 minus 1 minus 1 minus 1 minus 1 1 minus 1 1 minus 1. My output is 1 minus 2 minus 1 2 1 so on. My v. So my v is I put u and y together. So u and y together as u and y together. That's my v. Okay, that's my v. All right. Then my big v here. You can see that this is the first column is my u. That's my u here. That's my u here. And the second column, second row, the first row is my u here. The second row and third row will be my v. So if you look at this, my second row and the third row will be 1 1. That's 1 1 here, 1 1, and I have 0 0 there. And then minus 1 minus 2, minus 1 minus 2. And minus 1 minus 1 minus 1 minus 1, minus 1 2 minus 1 2 minus 1 minus 1 minus 1 minus 1 minus 1 minus 2 minus 1 minus 1 minus 2. So I put here only up to 1 2 3 4 5 6 1 2 3 4 5 6 7. I put only 7 data here, and I still have more. You can add more if you like. This v, you can add more. Now I just, for example, you can add all of them, or you can just put some of them there. But that's up to you. But most likely, we put all the data in there. So that's my v, and that's my another v. So when you form this v matrix, you have to be careful because you have some 0 0 there, 0 0 0 0 0 0, and those 0 0 0 0 represent the data before t equal to 0. For example, u That's beginning by t equal to 0, that's 1, 1. Before t equal to 0, then assume they're all 0, 0, 0, 0, 0. Okay, assume before the time equal to 0, then we don't have any motions. That means we have no motion of y. So, and we have no input u either. All right. So I have a dot, 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 dot here. If you look at this, I have a ray dot here. Look at the ray dot here. My ray dot here means on the left-hand side, and I have something, some data, 0, 0, 0, 0, 0, 0. There's some data involved on the left-hand side. And this is on the left-hand side, I assume that the system is not moving before time equal to 0. All right, that's I make assume that corresponding to, see, I have a red dot here, Okay, I have red dot here. That red dot here, that means this y1, y0 and y1, this two number y1 and y0. Okay, these two data, 1 and minus 2 data, these two data, they involve something that some data before time equal to 0, and that's so this I have a dot here. These two data, 1 and minus 1, so that involve something that the data 0, 0, 0, 0. Now, if your system is moving before time equal to 0, then we cannot assume that this 0, 0, 0, 0 there. So if that's the case, then what you can do is I say, okay, I can truncate those two columns out. I say, because I don't know those numbers, and I cannot assume they are 0. Then I can just say, oh no, I cannot use these two columns because I don't know the number there. If I cannot use these two columns, then that means this output at time equal to 0, output at time equal to 1, these two numbers I cannot use, there are 2. So I truncate those two numbers out. You can do that. And if that's the case, then we can do this. So in your homework, then that's my y. Assume this is initially at rest. Then your homework, I assume initially at rest. So your homework y bar, this y bar equal to that, the parameters, then equal to y v pseudo inverse. So y v pseudo inverse is this. This is the solutions. So if you solve in your homework, if you know how to form v, you know how to form v, then you will be able to solve your alpha and beta like this way. So this is the way to show you how to solve alpha and beta. All right, and you can just use the exact same action like this one here. And those the data you have, I give to you, those are very similar to data I put in these examples. So your homework 10 is very similar to this this example. You can just follow this example to form your V matrix to solve your alpha and beta. All right. As soon as you solve alpha and beta, then you will be able to do the output predictions. And there's a formula there. I'm going to skip on that because we already talked about that before. Then I'm going to jump to the example. So this one, I'm going to jump to the example. This example, the alpha beta, I solve it from observer Markov parameter. That's something I know. But in your homework, you solve alpha beta from the data. I just show you. Okay, that's so. After you solve the alpha and beta, this is the alpha beta. I just show you how to solve it from the data. Then after you solve the alpha beta, then you can use the formula like this to get the T matrix. you can use the formula like this to get your B matrix, and that gives you the B matrix. Of course, that now if you solve from the data, this will be a number, that will be a number, that will be a number, and this will be a number. Then you can solve, just follow this formula to do that. And I didn't have a chance to do all that for you from that example we have. The same thing, you can use this formula to solve the A, and A is just like that. And as soon as you solve that, then you will be able to form this called output prediction matrix. Then after you got an output prediction matrix, then you can solve these control equations, and that's the way you will do. And this is a very simple example in your homework 10. That's a very simple example there. So you can just follow the one. I just show you the new slide. I show you how to form V matrix. Then you solve from that V matrix, you solve alpha and beta. Then from that alpha and beta, you solve T matrix, B matrix, A matrix. And from there, then you can solve your control to get your control equation like this. And that's control equations. And also that in homework, I also assume Q equal to I here, and R equal to a scalar times the identity matrix. The same thing, exactly the same this formula, the same procedure, you follow this, and then you will be able to solve your control equations. All right? That's, I talked already here. Do you have any questions so far about your homework? 10? No, you have not started yet? Maybe not. You did. Okay, it's good. All right. Then this equation, you have to be very careful like this. Your homework here. I say your homework, I give you the system order is 2. That means n here equal 2. The system order. Okay. And then the disturbance state, I didn't give you a disturbance state, so that's 0. Your homework, the output number is m equal to 1. Because I have only one output, so m equal to 1. You have to know how to apply these equations, because this equation allow you to solve for p, the p. All right. So in your homework, n equal to 2, right? N disturbance state equal to 0. Your m equal to 1. So 2 divided by 1 is 2. So as long as you pick up p larger or equal to 2, that's enough. You can pick up 2, you can pick up 3, you can pick up 4, you can pick up 5. Okay? But 2 is minimum. So in your homework, if you want to pick up 2, fine with me. If you want to pick up 3, it's good too. Pick up 4, it's okay. Understand? It's up to you. All right. Now pick up 2 is the minimum, and that's easier to solve. Pick up 3, a little bit more complicated because your V matrix will be larger. Okay. Understand now? Okay. So you got to remember this formula, you know, and I'm sure that my final exam will use this formula. All right. If I ask you, say my system state is 10, my output number is 3, then what is the p, minimum p? 10 divided by 3, that's 3.3, right? 3.33. So what is the minimum p? 4. Yeah. So 4 is the minimum. It can be 4, can be 5, can be 6, can be 7, can be 8. All right. And on the other hand, if I give you, say, p equal to 2, I give you m equal to 1, then your what is your system states n? If I give you p equal to 2, and m equal to 1, and what is our system state? I can ask you another question. So I can give you p, I can give you m equal to 1, and 2 bounded by 1 is 2. So minimum, the maximum system state is how much? 2. Okay, that's the maximum. Because m multiplied by p, that becomes maximum. That 2 must be larger or equal to n system states. Right? So if I say p equal to 3, m equal to 3, then what is the maximum state? 9. Yeah. So that's the maximum system state is 9. It cannot be more than 9. All right. Understand now? You know how to. Disturbance states means something doesn't belong to your system state. That's like aerodynamics. That's you don't know. It come from somewhere else. And if I say number of disturbance states are 0, and number of system states are 5, and most of the time will be even number, like a 6. And I give you, say, the sensor output, number of sensors output is, number of sensor output is, say, 2. Then P, you get to pick up P. What is the P? All right. 6 divided by 2 is 3. So you have to pick up P minimum. That's a 3. That's a minimum P. That's 3. But you can pick up 4. You can pick up 5. It's okay, as long as you pick up minimum number. Okay, understand now? Okay, so n belongs to the system states. Another n disturbance state doesn't belong something coming to the system, but that's not a system state. That's from some other outside the source, like aerodynamics. So you have aerodynamic state. Okay. All right. So that's something that I'd like to tell you, and following that, control horizon and system prediction horizon, we in most of the cases we all use SP equal to P, SC equal to P, so they all equal to P. That's in practice, because there are too many numbers you can choose. Sometimes it's not a good idea. Okay. You don't worry about those. Those are based on our experience. Those are experience that we summarize all the GPC. Summarize all what we find for the GPC. Okay, a lot of sense. Low pass filtering and so on. I didn't even teach you how to do it. Micro frequencies. If you don't learn system ID, you may not know micro frequencies. What micro frequency means? That's from digital data. So you have some kind of micro frequencies and so on. So we don't worry about that for our lecture, because in very short period of time, there's no way for us to explain so many years experience. That's what we use before. But I will show you some of our real examples very soon. Okay, and there's something that made, for example, that the length of data, how many data you're supposed to have. For example, in your homework, I give you like a data equal to 10 or 5. In that example, my data is only 8 or 7. That's not a good number. When you try to solve alpha and beta, the data we use always like 1,000 or 10 or 100,000 data, a lot of data. All right. That's what we use, because the more data you use, then you can solve the better solutions for your alpha and beta. The reason is the data always got some noises, some uncertainties in the data. In other words, your sensors are not perfect. If your sensors are not perfect, then you expect to have some uncertainties in your sensors, and that's something that we have to use more data to be able to balance out or to be able to average out all the noises. Okay. All right. Let us look at the following example. The following example, we have we call lamped mass spring dashboard systems, like your TMD, and we show you the simulations. Then we also have experimental data, use Cobra stick model, and Cobra stick, Cobra, you know the Cobra, right? Helicopters. The 响尾蛇 the Cobra, yeah. That's the model, and we can use the Cobra model in the experiments. The Cobra model, the Cobra helicopter itself is not really stable helicopters. So the pilot has to be very careful, otherwise it can be unstable. If unstable, then it can crash. So you might heard a lot of stories about Cobra. They crash. And then we also will talk about the XP15. This is experimental data. This is XP15 is a simulation data. And then we'll talk about another called hover test of Steve implant rodent, we call rats. I will show you in the movie on the rats. And then we have more data about rats. And I will show you this. Now, if you look at this is the typical figures we use to show you the system is stable or unstable. Now, if you look at this carefully, this is the spring and dashboard mass, spring, dashboard mass, spring, dashboard mass. So we have 3 mass, 3 spring, 3 dashboard. There. Now, if your dashboard, this is simulation, this is not real sense. If your dashboard here, this dashboard is always positive value. For real dashboard, then this data is all positive value. This is all positive value, positive value, positive value. When you have one of them is negative, in real device it won't be negative. But assume in our simulations or computer simulation, we assume one of the data is a negative. Then what happens? The system becomes unstable. It's not stable system anymore. So this is what we call TMD. TMD won't be unstable. But this is simulations. We can assume that one of the dashboard is negative. This simulation is not real device. And then it will be unstable. This open loop response, that you can see that they are unstable. That means their response is growing, right? Their response is growing. That means we purposely put one of the dashboard value, the zeta 1 or zeta 2, zeta 3 negative. So it becomes unstable. All right. Now, from here, from 0 to 1 second, from 0 to 5 seconds, you can see from 0 to 5 seconds. We also have an external disturbance to the system. There's some external disturbance from U1, for example. The U1 is we give them external disturbances. That's not because of system. We give them like these periodic disturbances. So we give all the system disturbances. Like for example, I like to use earthquake. Earthquake gives you some periodic disturbances. Give you 101 periodic disturbances. And assume that we cannot measure that earthquake disturbances. we don't measure it. Then this open loop unstable plus disturbances, that is from 0 to 5 seconds, we have this unstable system plus disturbances. That's from 0 to 5 seconds. That's this one and that one. So from 0 to 5 seconds, we have the disturbances plus we have unstable system responses. That's from 0 to 5 seconds. Now, as soon as we have from 0 to 5 seconds, this is our one is our control input. Assume we give them control input here, very small control input, and that control input is say from U2. U1 is our disturbances. This give a U1. This U1 give our disturbances, just like earthquake. This U2 will be our control force, for example. All right, and then we measure at the W3. This is our measurement. Now our measurement output Y will include your open loop responses plus your disturbances, right? When you are 101, your earthquake, and your sensor put on the 86th floor, so you have the sensor there. The sensor will measure your system response plus the earthquake-induced responses, right? You have two kinds of responses. One is system responses. Another one is your earthquake-excited responses. So you have two responses involved in that. So that's this 0 to 5 seconds. So from 0 to 5 seconds, we have input, control input. That's your U. So in your example, I have U, right? In your control, I give U, right? That's the input. That's a control input. I give them very small control input. And that control input is some kind of random input. So in your example, it's some kind of random input. Okay? And so here we have input, where output is Y. So your input from 0 to 5 seconds, you don't see any signal here, but if you look carefully, there's a very small signal involved there, because this at 5 seconds, this is too much. I will explain why my control force become from almost 0 to like 30. All right, you know what happens? From 0 to 5 seconds, I have a control input and I have output Y. So I use those input and output Y. I identify alpha and beta. Understand what I'm saying? I have input U, I have output Y, and I can use that U and Y to form a big V matrix, right? From that big V matrix, I identify what? Alpha and beta. Identify alpha and beta, right? Then I identify alpha and beta. From alpha and beta, I can continue to solve my TBA, right? And from TBA, I can solve what? I can solve my UC, right? Right? I can solve my UC. So this 0 to 5 seconds, my job, the computer job is, I have an input data, I have output data, I form V matrix, I solve alpha and beta. And then from alpha beta, I solve TBA. From TBA, I solve what? I solve the UC. Agree? Now you switch here. So that's the step. So I have a control input U0, U1, U2 to U, say 1000, all right? That's my 5 seconds. So this is my 5 seconds. All right? Then I have output. Then that's my Y, 0, Y1, Y2, and I got Y1000. Right? Okay. So from these two, then I will be able to come to form the V matrix, right? To form V matrix. And Y and Y bar matrices. Then after that, I solve Y bar that's equal to beta 0, right? Beta 1 minus 1 R1, beta 2 minus alpha 2, and so on, right? I solve alpha and beta, right? Agree? Then after that, then I from Y, I solve what? I solve T, I solve A, I solve B, right? And after this, then I will be able to solve UCK, right? That UCK is equal to what? Equal to the alpha 1 C, then Y K minus 1 plus alpha 2 C Y K minus 2 plus alpha P C K minus B plus beta 1 C U K minus 1 plus beta 2 C U K minus 2 plus beta P C K minus B. Agree? So you got a control input, the 5-second control input, and 5-second output, a sensor output. Let me say this is called sensor output. All right, I got sensor output. The sensor output is Y0, Y1, Y2 to 1000. Assume that's my 5 second. I have 1000 data. Then I form the V matrix. I form Y and Y bar matrix. Then Y bar give me alpha and beta. From alpha beta, I can solve the TAB. From TAB, I will be able to solve my control input. This is my control input formulations. So I solve UCK, I solve. That's my control input. That's my process, right? And that means in 5 seconds, the computer has to, well, not in 5 seconds. After after I got 1000 data, the computer has to solve all this as soon as possible. Most likely, today's computer, you can solve this in a less than 0.001 second. Right. This is very quick if you write a very good form. And in our requirement, in NASA requirement, they want us to do this. They have to solve this within 1 second. And 1 second to us is very easy. Okay. So by today's computer. So when you look at the data there, the 5-second data, I have input, I have output. And then the output, this output include unknown disturbances, just like earthquake, we saw unknown disturbance coming to the system. And also your output responses. These responses, why include the responses from unknown disturbances and your system responses. Unknown disturbances, for example, just like earthquake, or like when you sit inside the airplane, then you have some disturbances from unknown disturbances from outside the air. From outside the air. Okay? You finish that? Okay? Then you can switch back. Okay, go ahead.
I want to know the dimension you see.
All right. The dimension of P, I think you want to know the P first. All right. The P is you use that formula. The P, if I don't know anything about my system order, all right. For example, this building 101. But now, how many frequencies of 101 below 15 hertz? Because disturbance come in, that disturbances, the Taiwan earthquake disturbances, the frequencies are less than 15 hertz. So, for example, 101, the building, by system frequencies, I expect the number of system frequencies which are less than 15 hertz. Say, assume 10. Can I assume that? No, you cannot. But the somebody built the 101, they have done some analysis. And from that analysis, they will be able to tell you. So under those 15 hertz, assume I have 10 frequencies for 101. Then if I have 10 frequencies for 101, then how many system states you have? I ask you. If I have 10 frequencies, how many system states I have? Now, each frequency is corresponding to 2 states. So you have 20 states, right? Okay. Then next question I ask you, how many sensors you put in the 101? Say, assume 1. Then what is the P you're supposed to have? Minimum P is what? Number of states divided by number of output. So that's 10, right? Minimum is 10. If you put 2 sensors at 101, M, that means equal to 2. So you have 20 states divided by 2. So how much? P? 10. Minimum is 10. I say minimum, but you can 10, you can put 20, you can put 30. As long as you put more than 10, you are safe. Okay? So that, I think that answers your questions. How much P you need, right? Then what you have to do is you have to determine how many frequencies you think in your system. All right? You can get that information from analysis, from any other documentations like that. If you say, well, I don't have any document like that, then what can I do? In matter of fact, you can still do it. You can choose 10, you can choose 20, you can choose 30, and compare it. As long as you want your P is increasing, that's fine. I understand now? So P can be randomly guessed. That's the message I want to tell you. You can guess a good number, like say 10, 20, 30, depending on how many number of sensors you have. For example, I say I pick up 10. I have a sensor I have 10 sensors. I have P is 10. I also have 10 sensors. Then what is the states I'm supposed to get? Number of states. P multiplied M, that's 100. So you expect your system state will be what? Will be 100. Understand now? Okay. So that is the what's going on here. So now you know how to choose it, right? Okay. The same thing here. Go back. go back to notes. Now you look at these notes. The first 5 seconds. The first 5 seconds is the time we take the data. The first 5 seconds we take the data, input data, and output data. So as soon as I got a 5 second data, so assume I have 1,000 data, then as my computer or the system won't stop. The systems continue to go, right? But your computer in that within then maybe at 1 second or 0.1 second, I have the computer RC, UC. As soon as I compute UC, then what I can do? I can turn on my controller, right? My UC here. This is the control input. I can turn on my control input like this. At 5 seconds, I turn on my control input. You will be able to see, well, look at, in the first very few seconds here, my control force will be very large. Because I'm controlling an unstable system. Okay? Because your control force is very large, then you can see my output become very small after 5 seconds. Because after 5 seconds, I turn on my controller. That controller I computed from the predictive control, the UC. So after 5 seconds, I turn on the controller. Here, turn on the controller. My system from these large responses jump very quickly to very small responses. But if you look at carefully, your output still have what? Still vibrating. Why? Because your disturbance is still there. Your earthquakes still come in. They don't stop yet. So you still have a small vibrating here, right? Your control force still have a control force in there. Did you see the control force after 5 seconds? Small, but it's still working. Okay, as long as you have a disturbance still going on, your control input, your control force still going on. Understand now? Okay, so this technique has advantages. Advantage is one, it can compute your control force, control your gain like a alpha C, beta C quickly. Allow you to turn on your controller in very short time. Don't forget that when your computer is working, your system is still working. They don't wait for you. You can say, hey, system, you wait for me. Let me compute my control force first. And you just wait for me. They can't do that, right? So you have to ask your computer, hey, get my control force as quick as possible, right? So that's what we did. So from 0 to 5 seconds, that's what we call the data acquisition time for system ID. Data acquisition means that's the time we are taking data, the input data and output data. And after 5 seconds, because computer already compute the control force, the alpha C and beta C, then I can turn off control. That's a time for us to what? That's a time for us to turn on the controller, and then your controller will go, and then jump. Your system response. So the 101 just like that. All right. So when the earthquake comes in, still shaking, but your 86 floor is not really shaking much because you have TMD control. That's the same reason like that. So this predictive control is a feedback control, but it's not a TMD. It's a feedback control. Okay. Do you understand this example now? So this example gives you an idea that the predictive control will be able to also control some unknown external disturbances. we call external disturbances mean we cannot measure it. We don't know when they come, just like earthquake. And we don't measure it. For example, if you don't have any accelerometers on the ground, we can measure how big the force coming from the earthquake. Agree? Yeah, like that. Okay. Let us take 10 minutes off, and then I talk about Cobra stick model.
因为这个算出变异题嘛，
对对，
这个反应先算出那个阿尔法贝塔，
对对对，
从那个双阿尔法贝塔算
会跟 O 的